Okay, hello everybody. Hello math majors. Hello graph theory enthusiasts. It's so great to see all of you again. Welcome to the 10th week of our semester. We've just about rounded the corner here. I know it's been a hectic time. You know, the average month has 22 work days, but October feels like it's had about 30. It's been a long month, but yeah, we're making it through, and I hope that you guys are doing well with everything. I just have a couple of quick comments, then we're going to jump right in today into some of the math here. Because we actually had like 10 classes in the month of October, but as soon as we get to November, it's like half as many. So I'll start to see the end of the semester come in a more accelerated pace. So I'm looking at my notes saying, yep, we got to keep moving, In terms of announcements, just two quick things. There is a homework assignment due this week on Thursday, like usual. And I do have office hours, of course, on Thursday. I have them tonight as well. However, this is my once a month. You all saw me giving an exam, right? It's my once a month nightmare or a stack of papers deal. So you might remember last month, whatever day that was, I basically stopped down at my office for about, 30-45 minutes or something. And then I basically skipped town to grade for the whole rest of the night and the rest of the day. So if you don't mind, I would like to do that today as well. I'd like to have a fairly short office hour. If you have some questions that you've already developed for me for today, if you could try to swing down there right after class, I'll try to hang around for 30-45 minutes or so, and then I'm probably going to try to disappear and get those papers graded because it will take me forever, all the way through tomorrow for sure. So, but then Thursday should be good. We should have plenty of time on Thursday to finish more questions if you have any. Okay, so that's the homework and the office hour story. And I think that's about all I've got for announcements for now. So on the board over here, and I know I barely let you guys in the room to even look at this yet, but what I put up on the recap here are just some of these terms that, this is actually more of a recap of that video that I had you watch than anything we did in class last Thursday. There's all these words that kind of run together and can be a little confusing, like what is a walk, what is a trail, what is a path? These kinds of things. And so I just wanted to remind you here, this might be flashcard material if that's the way you learn your definitions. Kind of write these down and shuffle them up and keep them straight because they are very similar. The most general word that's on the board up here is the idea of a walk. A walk is literally just a sequence of edges, and there's no conditions about that sequence. Just walking through the graph, literally from one vertex to the next, to the next, to the next. And if you end back up at the end of your walk at the same place that you started your walk, then it's a closed walk, right? So that is an optional property, of course. But you'll often see me, instead of writing my edges like this is the notation, of course, for an edge. You just write down two vertices and put them into a set. But a lot of times what you're going to see me do is just kind of do something like this. I'm walking from x0 to x1, so I'll just draw that with an arrow pointing from x0 to x1. Totally okay to do that, all right? So there shouldn't be any confusion with that. But that's the idea of a walk. Any sequence of m consecutive edges, that's a walk of length m, right? The only thing is you can't jump around in the graph, right? So whatever vertex you're at, you then have to follow an edge that comes from that vertex if you want to walk somewhere, right? You can't walk to a place that there's no edge. Okay, it's pretty common sense. And then we have the idea of a trail, which is just a walk that does not repeat any edges. So as long as you don't walk back along the same edge more than once, you have what would be called a trail. And then the related concept is a path. So we have to keep these two straight. A path is a walk that has no repeated vertices. So in this case, right, you're visiting the different vertices of the graph and you just can't go back to the same vertex more than once. Notice that every path would have to be a trail because, well, if something was not a trail, then it would not be a path. Because if it was not a trail, that would mean you were repeating the same edge. You walked on the same edge multiple times. Well, that would mean that you visited the vertices that that edge connects with more than one time. Does that make some sense? So I almost think of this note here. I like to sort of explain it in contrapositive form. So if something fails to be a trail, then it will fail to be a path as well. Okay, because if you repeat edges, then you of course are also repeating vertices. But it is possible to repeat vertices without repeating edges. And I'm sure that in the video I probably drew a graph of something like that. So here's a graph, and we can visit this vertex here, V, several times without ever repeating an edge. We can literally just go around each edge one time, but we've visited that central vertex multiple times while we were doing that little figure 8 shape or whatever, right? So that's kind of the idea. So it is possible to have a trail where I have not repeated any edges, but which is not a path because I have repeated vertices. Okay. Makes sense, right? You can drive around on different you can come back to Fullerton 100 times without ever being on the same freeway more than once. This is not like my hometown, Nebraska, where there's one road in and one road out. But in these large metropolises, you certainly could do that. Nikolai?
So if a block is closed,
Yeah.
if it started at E, this example,
Uh-huh.
it would be closed multiple. Because it would hit the same.
You could say that, but all we're really going to do with this definition is look at where we started at the very beginning and where we ended up at the very end, and it's either thumbs up or thumbs down if it's closed or not. But you're right. Yeah, there could be some sub walks that are actually closed within the big longer walk. Absolutely. By the way, a closed path is called a cycle. So we will see that terminology a lot as well. So these are just some of the buzzwords that I know I went over them in the video that you watched last week, but now we're going to use them now, and I wanted to get them kind of up in front of us again and make sure we can kind of see the differences between them. So what I want to talk about next is the idea of trying to walk around on this graph that we have, whatever the graph is, in such a way that we only walk on so that we only walk on edges once, and such that we use every edge. Okay, so this is somehow a nice practical problem, a practical application. Let's say that I would like to, visit, the country. I'm driving around on the highways, and I want to see all of the scenery exactly once. I don't want to duplicate. I don't want to be inefficient in doing it, but I do want to see everything, right? So that's actually a concept in graph theory, and there's a definition for this, which is called Eulerian trails. So I'm going to be going into, just so you're aware, in the book, this is section 11.2, is called Eulerian trails. So this is what we're going to talk about here today, guys. 11.2. Okay, so Eulerian trails. We'll start with this concept, and then there'll be something similar to it for paths as well. So let me just draw a graph up here just to kind of inspire us a little bit. Let's suppose that I'll just start by drawing a graph. You might have to follow along here and make sure you're getting this graph drawn correctly. I'm going to start with two vertices A and B, and I'm going to connect them by two edges that go between A and B. So this is actually what's called a multigraph, right? And then somewhere over here, we have another vertex, which I'll call C, and I can kind of make a triangle from A to B to C like that. And then I'm going to draw another vertex over here, which I'm going to call D. I'll draw another edge here from C to D. And then I'm going to draw another edge from D down to an additional vertex E. And let's see, what else do I want to have? Then I'm going to make another vertex up here, which I'll call F. I'm actually going to put a loop on F. So this is what's called a general graph. And then from F, we're going to have one more vertex, which will be G, which I'm going to put over here on the far side. And G is going to connect actually back up to C again. So there'll be another another edge there. I think I got my whole graph drawn now. So that's an example of a graph that we'd like to play with here for a moment. And so the question that we're going to ask about graphs today in this section 11.2, the main question that we want to answer is, can we find a trail? Can we find a trail in the graph, right, using every edge exactly once? So that's the key thing. Exactly once. Okay, so a trail should not have any repeated edges. So that means I'm never going to use an edge more than once if I want to have a trail at all. But even better than that, we actually do want to use every edge. Okay, so it's got to be every edge, no more than once, but now at least once. So that means exactly once. That's the definition. Yes.
Quick question, is the whole graph a multigraph because of A and B connecting?
Yes, yes, as long as you have any two vertices that have multiple edges between them, we would call that whole graph a multigraph. Yeah. Okay. So a quick remark here. I'll start with something I think is fairly obvious, but we'll write it down anyway for the notes, which is that in order to have an Eulerian trail, your graph has to be connected. If the graph has disconnected pieces, then you wouldn't be able to do this at all. So Eulerian trails, this is a quick remark here. Eulerian trails can only exist in connected graphs. Now, one of the questions that we will be asking is, I'll give you a graph and I'll ask you, does there exist an Eulerian trail? So if the graph is not connected, then the answer would definitely be no. Also, these trails could be closed, but they don't have to be. Closed just means that you end up back where you started again. So it is possible to take every highway in the US, right? So you cover every edge, but you don't end up back where you started, right? So we're going to actually talk about that case first. So our first scenario that we're going to look at here, guys, this is probably the easier scenario to think about, is just looking for closed Eulerian trails. So the first scenario, I want to look for a closed Eulerian trail. So this will be a walk that is a trail that is closed and which uses every edge exactly once. Okay, so maybe we can try it out on our example up here. We've got a graph to look at already. It turns out that if you're going to have a closed Eulerian trail, it doesn't really matter where you begin or where you end. So we could begin anywhere that we wanted. Maybe I will choose to begin at A. Okay, so I'm going to try in blue. If this blue marker shows up, I will try to trace out a closed Eulerian trail. So in the graph above, let's just see if we can do it. Let's just say that we're going to start at A. And again, I'm going to use my little informal notation of drawing arrows that represent the edges. And I want you guys to help me try to make an Eulerian trail. So let's see if we can call on some people today to help me. So if I start at vertex A, Eduardo, where would you like me to walk to first? I'll let you choose.
What if we go to B?
We're going to go to B. We actually have two ways to get there. Let's just pick one of those edges. So let's say we're going to go to B. And so I'll put that over here. So we go from A to B. All right. Luke, if I'm standing at B, where would you like me to go next?
C.
Okay, we can go to C, for example. All right. All right, so we'll go from B to C. The goal here is to try to use every edge without repeating an edge. We cannot, no repeated edges, but we'd like to use every edge. Okay, so Abby, if I'm, now I'm at C, where would you like me to head next?
G.
G, okay, so from C, we can go all the way over to G here. So far, you guys are playing nice. We get to from C to G. And let's see, where do you want me to go from G? F. I actually have to go to F, right? Because I only have one more edge I can use. This is part of the idea, is that anytime you enter a vertex along your Eulerian trail, you will have to have another edge available to leave that vertex, unless it's the starting point or the ending point. So I do need to use this edge here from G up to F. I hope you guys can see. Hopefully my marker is good enough right now. So from G to F, we've got that. Okay, so I'm standing at F, and Khalil, where would you like me to go from F? Let's loop back to F again. Okay, as long as we're here, let's just take that little loop and we go back to F again. So I'm just gonna draw that as an edge from F to F. It's really just a loop. And so now I'm at F again, and Keshik, where would you like me to go from F now?
To E.
I have to go to E. So F goes to E. And actually, you can see from there, I have to go back to D. So I'll go ahead and take that move as well. So from there, I go back to D. And then once I'm at D, I actually have to go back to C. All right, so from D, I will go back to C. And when I'm back to C, where can I go from there? I have to go back to A, right? So C goes back to A. And once I'm at A, where am I going to go? Back to B. That's the only edge that's left. Look at that. I was able to do it. So let me finish my little trail here. C went back to A, which then went back to B. Exactly. Okay, so this is an open, okay, Eulerian trail. So I will point out here that this one we did not start and end at the same point. Would we have been able to start and end at the same point, do you think?
Yeah.
By starting where? Uh-huh. So if I started at A, went to B, and then went back to A, I'd have to leave A again, wouldn't I? Right? Would I be able to then get back to A again? Yeah, okay, so are we realizing here, guys, that whenever you enter a vertex, you also have to be able to leave that vertex, right? It's actually a very simple condition, which is that you need the degree of the vertices to be even. If the degrees of the vertices are odd, then you won't be able to keep, every time you enter, you have to leave. So the number of edges that is incident with a particular vertex would have to be even, except for the first and last vertices. If you take a look at this graph, all of the vertices have even degree except for A and B. Now, if I made another edge, okay, if I made one more edge between A and B, then I could do it, right? Then if I'm at B, I could then follow this edge back to A again, right? And then I would have a closed Eulerian trail. So guys, that is our first theorem. A graph will have a closed Eulerian trail if and only if it is connected and every vertex has even degree. It's an easy test. It's an easy test. So let's actually write that down. So this is theorem 11.2.2. Okay, let's see what this says. Okay, so let's let G be a connected general graph. So it's okay if the graph has loops or multiple edges. That's not really a big issue for this concept. Okay, then here is my statement. G has a closed Eulerian trail if and only if every vertex has even degree. If and only if every vertex has even degree. So I'll kind of highlight that here, and I am actually going to write up a proof of this. Even though it's kind of intuitively clear, but it's worth writing it down as well, since we're just getting used to this new idea here. So the proof, oh, and then if you would like to have an open Eulerian trail, which is gonna be the next theorem, I'll write it down in a moment, you have to have exactly two vertices of odd degree, which this graph does, right? If you look at the degrees here, we have three. No, we don't have, sorry, I'm getting rid of this edge again. This was three, 4, 2, 2. A loop contributes 2, right, to the degree, and this is 2. So there's exactly two vertices of odd degree, so there's no closed Eulerian trail here, but there is an open one. Was there a hand up somewhere? Yeah, Lindsay?
Open the.
Correct, right. We started at A and we ended up at a different vertex B. That's right, that's right. Okay, so let's write down the proof of this theorem. This is if and only if, so I'm going to do it in both directions. There's a forward and a backwards part that we should write up right now. So I'm gonna start by assuming that G has a closed Eulerian trail. Okay, so we'll start with that assumption, and we're gonna try to prove that every vertex has even degree. Okay, so let's pick a vertex. So let's pick a vertex. I'll just call it little v, which is an element of capital V. Remember, capital V is just the vertex set that we have. Okay, and we're gonna try to show that the degree of V is even. And it really just amounts to the following observation. Each time our trail visits vertex V, every time it visits that vertex, right, two distinct edges, and I'll add here in parentheses, or a loop, are used. So it could be a loop. We saw that there was a loop in our example a moment ago. So you're either going to go around a loop or you're going to use two distinct edges. Okay. So if V is visited K times in total, if it's visited K times by the closed Eulerian trail, it's just a little paragraph actually. If it is visited K times by our closed Eulerian trail, then the degree of the vertex is just 2K. It's just 2K, which is even, right? Exactly. So you can come over here and take a look. Just as an example, we visited the vertex C 2 times during this Eulerian trail. So that means the degree of C should have been 4, right? We visited the vertex F 2 times, and the degree of F was twice that. Right? It's always just double whatever the number of visits is. So you just look how many times does that vertex appear in your trail, double it, that'll be the degree of the vertex. So it's gotta be even in this case. So that's the forward direction. If we have a closed Eulerian trail, then every vertex V has even degree. Clear enough? It's kind of just a sentence or two. Okay, one of the things I think that people find a little weird with graph theory is there's not a lot of equations here. We're not just manipulating formulas. It's mostly just kind of conceptual stuff that we have to reason through. I now have to explain the backwards direction of this same result. So if every vertex has even degree, we have to explain why that means that we can make a closed Eulerian trail. And what this is going to be basically is a blueprint for how to make the closed Eulerian trail. Okay, and actually the good news about this, believe it or not, is you almost don't even have to turn on your brain. I noticed when I was asking people for where do you want to go next, people were like, ooh, I wonder what I should pick. I don't want to mess this up. It turns out you almost can't mess it up. And this reverse algorithm will show you that, so that you pretty safely can come up with an Eulerian trail without a whole lot of stress. So here is how that would come out in I'll call this an algorithm. The backwards direction is essentially an algorithm. Jose?
These little side connections, usually like on, you ever use TikTok, there's like a game where like all connect like without repeating like badge.
Uh-huh.
I just thought like, oh, this is what we're doing.
It's a practical application for sure. You're gonna see this kind of problem. Constructing Eulerian trails in graphs is something that is important for everywhere from computer science to the physical world we're living in. So it's not a big surprise that we're finding games that model this as well. So let's assume that the degree of V is even for all vertices little v in capital V. So suppose every vertex has even degree. And what I'm gonna do is I'm going to choose a vertex. I'll call it a V0, a specific one. I kind of like here, I chose A, which is where I started my trail from. This is basically what I'm gonna do. I'm gonna show you how do you construct the trail. And by the way, there's not a unique answer here. Okay, so how do you construct the trail? Well, choose a vertex V0 and then choose any edge. And I'll write my edge as V0 and V1. So this would be an element of the edge set. How do you know that there is an edge to choose at all? Well, if there wasn't, then the vertex would have been isolated and the graph would not have been connected. So it has to be possible to find such an edge. This is not a concern really. So we can choose such an edge. By the way, notice I'm not saying that, you know, what kind of vertex this is. You can just we happen to start our Eulerian trail at A, but in theory, we could have started anywhere in the graph. This does not presuppose where this trail starts or finishes or anything. So just choose an edge. Now, since the degree of V1 is even, then that means that if I've used this edge from V0 to V1 to sort of enter the vertex V1, there has to be at least one more edge still available to leave V1 along, right? So we can choose another edge incident with V1. We can choose another edge incident with V1. Let's just say it's the edge from V1 to V2. And continue this process. Right, so maybe over in the margin of your proof here, you might want to just draw yourself a little picture. You know, you entered V1 along this edge from V0 to V1, but you've always got to be able to leave that edge or leave that vertex as well along some other edge. Okay, so this is the idea. So we repeat this process, right? Just keep doing it. Once you enter V2, since the degree of V2 is even, there has to be another edge available for you to leave V2. And so then you go to V3. You enter V3 along one edge, there has to be another edge that you can leave V3, right? So then you go to V4 and you just keep doing this forever. Now, there are some issues that can come up here that I'm going to address with this, which did not come up because you guys were really good when you gave me the Eulerian trail on the first example here. But, you know, you might wonder, well, could you kind of find yourself on an island back where you started with no more edges available, and yet there were other edges way elsewhere in the graph that you haven't used yet? And that could be an issue. So I have to address that. So let's just say this, since, just kind of an explanation of what's going on, since each vertex has even degree, right? Since each vertex has even degree, every edge arrives at a vertex. You go to a new vertex along an edge that can be followed. This is just kind of an explanation. That can be followed by a departing edge. So I can do a departure as well. And so you just keep doing that, keep using the edges up like so. But it is possible that at some point you will create a cycle and you'll be back sort of where you started. So whenever a cycle is created, right, what we can do is we can remove it. We can just fully remove the whole cycle. I'll show you in a moment with an example. But we can fully remove that cycle and then just start over building a new Eulerian trail on the graph that now has fewer edges. It's a smaller graph, so it'll be that much easier to then trace out an Eulerian trail on the edges that are still remaining. So we can remove it, leaving a subgraph. Whose vertices all still have even degree. And then you just keep repeating that process. If the trail returns to V naught before all of the edges are used. Come back up here again. Oops, maybe I want to keep this graph for another minute. Before all edges are used, so if we get back to the initial vertex before all the edges are used, which means we're not done yet, then we can just start creating a smaller closed Eulerian trail with the edges that remain, right? So then what we can do is a smaller, meaning fewer edges, right? A smaller closed Eulerian trail can be made, or let's say it this way, can be inserted. I think that's a better word. Can be inserted starting from a vertex, I'm going to call the vertex W this time, incident with some unused edge. That's a lot of writing. I'm gonna show it on this example. You guys didn't have that issue come up. The Eulerian trail that you gave me did not actually create that issue. So actually, to really do a good example, I should make sure that all of the vertices have even degree. So one way to do that would be to just take this original graph and just add an edge from A to B. But I could also just start over with a new graph. I think maybe I'll just start over with a new graph. So make a new example here to illustrate this. Let's make it an easier graph to play with. Suppose we have this square here. Like so, yeah, Fernando?
Quick in the proof, what makes, so when you have this sentence that says whenever a cycle is created, you
Yeah.
can remove it, leaving a subgraph whose vertices are still have the same degree.
Yeah,
What makes that different than when the trail returns to V naught? Is that not what happens there?
that's one way that it could happen, but it could also happen within the whole Eulerian trail as well at some intermediate point. So let me show you. That's why I want to do this example. So let's suppose we have this picture here, guys. So I basically have a square and then I have two triangles hanging off of it. And I'll label these vertices again. The square could be A, B, C, and then D in the middle. And then over here we go to E and F, and then down here we go to G and H, something like that. This time, all of the vertices have even degree. So if you believe, and it's a connected graph. So if you believe my theorem, there should exist a closed Eulerian trail for this graph, just looking at the degrees of the vertices. So this time we can start wherever we want. Let's say that I choose to according to the proof, I can choose any vertex that I want. And I just want to follow what the proof is saying. It says choose any edge. Okay, so I start with A, I choose an edge. You guys are playing too nice with this thing, so I'm gonna take over now and choose the edges. Okay. You really don't have to turn your brain on too hard for this because you really can't screw it up. I'll show you why. You might say, well, I entered B along one edge, so then because the degree of B is even, I have to be able to leave that vertex along another edge. But let's say that I don't play very smart here. I'm sorry?
Instead of C, it's gonna be D.
Oh, it's D. B to D. Sorry. Thank you. Yeah, thank you. Let's say that I don't play very smart here and I decide to take the edge from D over to C next. That's what my brain's already thinking about. And then let's say, well, now once I've entered C, then I have to go back to A, you see. Right? And you look at that and say, oh, well, now I'm back at A and I have nowhere to go. I'm stuck because I can't use those edges again. Anything that's blue cannot be used, but I didn't trace out all the edges so far. So that's where this comment says, if the trail returns to the original vertex before all of the edges are used, then you can create a smaller closed Eulerian trail, inserting it from some other vertex that's incident with an unused edge. So I come over here, I find some edge that I haven't used yet. And I pick any vertex that's incident with an unused edge. So in this case, I would probably look at my D because I want to insert this edge, let's say from D to E. And what I could do is I could draw it like this. I'm going to go from D to E. And then from E, of course, I have to go to F. Just draw it like this. And then from F, I have to go back to D again. And I'm still not done because I have another little triangle that hasn't been worked on. So the next thing I have to do is from D, I have to go down and hit either H or G. I'll go to G first, so D to G, and then G to H, and then H back to D. G to H, and then H back to D. So it will look something like that. And I'm okay if you draw your Eulerian trails like this with these inserted cycles off on the sides like that. That's totally, I can understand exactly what that means. Nikolai?
If I were to write it in a set notation,
Totally okay. In fact, some ways it's a little bit better. How would it look? Well, it would just be, so you'd start off A to B like this. And then you just comma, and then B to D, then comma, D to E, and so on.
and so you just put those triangle pieces.
Uh-huh.
in between.
Just put them right along the way in your list. Yeah, exactly. But this would definitely take more time. Like if you went back to A too prematurely and then you realize, oh, now I want to insert some other edges, then you literally have to do an insert. You can't just go off on the side and finish your little trail there. Yeah. Okay, does this make sense? Did I address this okay for the most part?
The only thing that I feel like, I guess just in the proof, I
Mm-hmm.
feel like whenever a cycle is created, that would in a sense be the case when the trail returns to D1. In a sense,
Whenever a cycle is created.
like the trail will return to the original position, so I feel like
Yeah,
it's like the same scenarios, but it makes sense, yeah,
okay, good.
it makes sense.
Khalil?
So in our original example, we would have gotten in trouble if we went, like, say we went from A to B,
Uh-huh.
and went to C,
Yeah.
then we went to G,
Oh, gee, uh-huh.
and then we went to F,
F.
and then we went straight to E instead of B.
If we didn't use the loop, see, you played nice, you picked the loop, but if you had not picked that loop, then we would have eventually ended up at B and we would have used every edge except for the loop. So then we would have to go back and insert. Just the loop would be the insert that you would do at that spot. Right, so you can always go back. So you can turn off your brain and just start following edges that you haven't used so far, as long as you're willing to go back and do a little bit of cleanup with edges that you didn't get used in the process of forming the closed trail in the first place. So you do sometimes have to go back and finish up, but you generally don't have to start over. You don't have to like say, oh, this didn't work, I have to start from the beginning again. You just take where you are at now and insert some smaller Eulerian trail within it. It's basically what this is saying. There's a smaller closed Eulerian trail that you can insert to build out the whole thing. Right. Yes, question.
So if we are letting, like, just from here.
Okay. Yeah.
But we only have. Beam. Vertices, would that mean that?
Oh, you just talking about a graph with only one vertex? Yeah, I mean, you would have to have a loop and, I mean, you could have several loops. And you could knock yourself out following those loops all day long. But yeah, there wouldn't be much to those trails. Yeah, so that would basically be it. Okay, so then there is, of course, the related theorem. I think I can state it over here. Is everybody with me? Any questions on this? So it's really easy. If I give you a graph and I ask you, does it have a closed Eulerian trail? All you gotta do is make sure it's connected and then check the degree of every vertex. Those are two very easy things to just look at to figure out. There's the related theorem, which is more relevant for the first graph we drew, is about open Eulerian trails. So let me state that one here. This is the very next theorem, 11.2.3. And this one says that, let G be a connected plane, connected general graph, connected general graph. Okay, so then G has an open Eulerian trail. Open literally in this context just means not closed. Anybody taking topology, please don't give me a hard time. It's possible the opposite of closed isn't always open, but in this case, that is what I mean. Open Eulerian trail if and only if G contains exactly two vertices of odd degree. Exactly two. And just as a note, just as a little sort of footnote here on this statement, the two odd degree vertices has to be the starting and ending points of the trail. There's no other option. So the two odd degree vertices must be at the start / finish of the Eulerian trail in this case. Right. The proof of this is pretty clear because all you have to do is, okay, let's suppose you have a graph that has exactly two vertices of odd degree. You just do what I did a few minutes ago, which is you just create a new edge between those two vertices of odd degree. Now they all have even degree. Every vertex has even degree, so there will be a closed Eulerian trail now in this new graph that includes the dotted edge, right? So you can make this closed Eulerian trail, and then you just simply pluck out that edge again. After you created the trail, you just remove that edge. It breaks your cycle. It breaks your closed path somewhere, and at that point, then what you're left with is an open Eulerian trail. So that's how you get your open Eulerian trail when you have two vertices of odd degree. You just imagine that you've inserted the edge between those two vertices of odd degree. Then you know there exists, if you believe the first theorem, there must then exist a closed Eulerian trail, but one of the edges of that closed trail is the one that you artificially had inserted. But you'll then remove that extra edge and it'll leave you with an open Eulerian trail. It's just that simple. And it is a nice thing if you know that there's two vertices of odd degree, that's where you can start and end your open Eulerian trail. Let me just maybe play with one more example while we're thinking about these ideas here. And again, this is extremely easy to just look at it and tell whether there's gonna be an open Eulerian trail or not. By the way, there cannot be both an open and a closed Eulerian trail in any graph. Because you can't have all of the vertices being of even degree, but then also have exactly two that have odd degree. So it's one or the other or neither. You're not gonna get them both. So let's just draw another graph and just see what we can say about it. Right, so here's just one more example of this idea, and then we'll move on. I'm just gonna make a fairly large square here on the outside because I want to put another vertex directly in the center of the square. And I'm going to connect all four corners of the big square into the center. And then I'm actually going to add multiple edges connecting two of the four vertices on the edge that are in the lower left corner and the upper right corner. And then let me label my vertices as A, B, C, D, and E. And I'm just going to ask, does this graph have an Eulerian trail? And I'll put in parentheses here, we don't care, either open or closed. Maybe either one is okay. So just to practice the theorem really quickly, this is a pretty easy theorem, well, both of the theorems side by side. What would you probably do first here, guys? Find the degrees of all the vertices. Yeah, that's all you really need to do. So let's see, vertex A has 3 edges incident with it. Vertex B has 4. Vertex D has 3. Vertex C has 4. And E has 6. So based on that, with those degrees that I wrote down in blue, would this graph have either an open or closed Eulerian trail? It would have an open one, right? So there exists an open Eulerian trail. So I'll say, yes, an open Eulerian trail. And let's, just since we've already got it up here, we might as well try and write one down. Okay, so I'm gonna start, well, Jose, give me a vertex that you want me to start at.
3, but I had a slight question.
No, I need a letter, not a number.
Oh, sorry, 8.
Hey, okay, start it. You have a question?
Yeah, well, what do neither look like?
Well, neither would be you have a whole bunch of vertices of odd degree. You have a graph that has like more than 2 vertices of odd degree. It'll definitely be neither.
Oh, okay.
Yeah. By the way, remember you can't actually have exactly 1 vertex of odd degree. Can you remind me why? If you have a graph with exactly 1 vertex of odd degree, let's see, I think we remember the handshaking theorem, right? We add up the degrees of all the vertices. That was supposed to be 2 times the number of edges.
Yeah.
This is the handshaking theorem. This is an even number. So you could not have just 1 odd number and then a bunch of even numbers added to it. That would not add up to an even number. So you can't have only 1 vertex of odd degree, but you could have, you know, some other larger number. You could have 18 vertices of odd degree, and that would not contradict the handshake. Right. Okay, is that good, Jose?
Yeah, that makes sense.
Sweet. Okay, so we're gonna start at A. Kevin, tell me, where do you want to go first? B. Okay, we're gonna go from A to B. That means I'm gonna use this edge right here. Let's do this kind of quickly. Luke, where do you want to go from B?
D.
D. All right, we'll go down here to D. Sounds good to me. We'll go to D. Maddie, where do you want to go from D? Over to C. Okay, go back to C. All right, and Austin, where do you want to go from C? E?
Yeah.
All right, we'll go to E next. You guys are playing so nice today. Okay, Christian, I'm standing at E. Where do you want me to go next?
A.
Back to A. Okay, so we're gonna go back to A here. All right, so we go to A. And let's see, Diego, where do you want to go from A?
We can only go to C.
We can only go to C. Okay, but then we better go to C. So we'll go to C next. And then from C, Fernando, where do you want to go from C?
To E.
Back to E, it's the only place I can go. All right, so we go to E. After we go to E, we need to go somewhere. Jasmine, where do you want to go from E? B, okay, so we'll go up to B. And once we're at B, Julie, where am I gonna go from B? To E, have to go to E pretty much. And then once we're at E, we only have one edge left, don't we?
Yeah.
Which takes us to D. All right, there it is. You guys played perfectly. I thought somebody would take me back to A or take me to D too soon and have to like insert some other cycle. We didn't have to insert anything here. It works, doesn't it? Yeah, you don't actually have to think too hard about that. Is everybody good with Eulerian trails? Pretty straightforward. Okay, so then you're ready for something a little harder. There's of course a similar concept for visiting every vertex of the graph exactly once. Instead of trying to hit every edge exactly once, I don't care which highways I take along the way, but I want to hit every city in the US or something like that, right? Exactly once. So that's a slightly different concept. Of course, that has to do with a path rather than a trail. A path, remember, is just a walk that does not repeat any vertex. Okay, so let's talk about that. This is actually in the next section. Let's jump ahead here, 11.3. And we're going to talk about something called Hamilton paths and cycles. Remember, a cycle is just a closed path, so it's really all part of the same conversation here. So we know that a closed path is a cycle, and we know that a path just visits every vertex at most once. You cannot repeat a vertex. Okay, so here's the definition that we are going to play with next. And this is also full of practical applications to computer science and the physical world. A path, and in parentheses, I'm going to say, or cycle, right? Which visits every vertex exactly once is called a Hamilton path. A Hamilton path, or if we're talking about a closed path, it would be a Hamilton cycle. So a Hamilton path or cycle visits every vertex exactly one time. So let's do a quick example of this as well. So I'm going to draw another graph. This is going to be like a mesh graph where I'm just going to draw like a 3x3 grid. So it's going to have sort of 3 layers here, both vertically and horizontally. We'll just draw this thing as such. So 3 rows, 3 columns. And then I'm going to label the vertices A, B, C on top. And then the middle row will be D, E, and F. And then the bottom row will be G, H, and I. So that's my graph that I'd like to play with, except that I'm going to add a few more edges now. So I'm going to add an edge from A to E. I'm going to add an edge from E to C, and from G to E, and from E to I. I'll just make this graph like so. So it cuts it up into a bunch of small little triangles here. I guess before we do the Hamilton path and cycle topic, which is sort of what we're moving into, we might as well, since it's so easy, decide whether this thing would have an Eulerian trail, either open or closed. Start counting out the degrees of the vertices. 3, 3, 3, 3, way too many odd degree vertices, right? This is a big no. You would not be able to do it. So there's just, as a little remark here, I'll just say as a remark, there is no Eulerian trails of any kind. So this is kind of, Jose, this is answering your question with a very specific example. There's a graph that has no Eulerian trails, open or closed, because all of the vertices pretty much have odd degree. Except for E, I guess. Okay, so there's a lot of odd degree vertices. But let's talk about a Hamilton path or cycle. Let's see, maybe we can start with a Hamilton path. So a Hamilton path, this should be a path through the graph. I have to hit every vertex exactly once. So let's get some thoughts down from everybody here again. Where would you like to start my Hamilton path from? Anybody? I'll start with A again. We could start from anywhere and attempt to do this, but let's start with from A, and I need to take an edge here. So what edge would you like me to take first? By the way, this time you can't turn off your brain like before. This time we have to do it smart or we might mess it up. So no pressure. You want to go to E? From A to E?
B.
Oh, B. Okay, yeah, we can go to B. All right, so we'll go from A to B. That's fine. We're trying to visit every vertex. So after I get to B, let's see. Eduardo, where do you want to go from B? To E. Okay, we're gonna go right down to E right here. I like that. So we have visited E. Once we have visited E, Maria, where would you like to go from E?
D.
Back to D. Okay, so we'll go over this way. We go from E to D. By the way, there's lots of right answers. Okay, so keep in mind, we're all doing this collectively. So we're just writing down one answer here. Mitchell, where would you like to go from D? Okay, so then we're visiting A for a second time, right? The idea here is we're only supposed to visit every vertex exactly once. So I don't want to go back to A again unless it's the end of a closed cycle, and which that would be a Hamilton cycle. But I'm not done with visiting the other vertices yet. So can we pick a different idea? Yeah, I guess in that case, I might as well go down here to G. Okay, so I'll go to G next. All right, so now we're at G and we don't want to visit E again. We've already been there once, so we really would want to go from G to H now. We'll go over here to H. Okay, so thinking ahead, let's just make sure we're going to hit every vertex. Once we're at H, where can I go from there?
You only have one option.
Only one option. I have to go to I. In fact, whoever visited E right away is forcing us to stay on the outside of the rest of the graph, which is fine. So we'll go to I, and then from I, we'll go back up to F, right? And then once we get to F, we'll go to C. And that should be every vertex. It's not a closed Hamilton cycle, but it is a Hamilton path. It is actually a Hamilton path. And as it turns out, for reasons that we will soon be understanding, this graph actually does not have a closed Hamilton path. It does not have what's called a Hamilton cycle. So there is no Hamilton cycle in this graph. So we have to develop some intuition behind that to understand why you could not actually get back to the starting point again in this process. So that's something to come in what we're going to do next. I'm going to write down a few observations here. I just love that for the Eulerian trails, we have these theorems to just apply directly. The Hamilton path topic and Hamilton cycle topic is much more challenging. And I would actually point out that there are a lot of still open problems about Hamilton cycles. I do not have a one size fits all theorem like we do over here that's going to tell us when there's going to be a Hamilton cycle. You look like you want to ask something. Please do. Go ahead.
For a Hamilton cycle, how is that ever possible? Because you have to like finish where you started.
So you're going to allow yourself to revisit the vertex that you started from. So I understand it says here you're not supposed to visit a vertex more than once, but we will kind of as an exception, we'll say that it's okay to end up back at the starting vertex again. Yeah, Nikolai.
Couldn't you just go? Say, starting at.
Yeah,
then
you could,
E, and then you go to E.
and then back to A.
Oh.
F, I, H.
Oh, I think you're right. Okay, so hold on. I think you're right. Oh, I know. Of course we can do this. Yeah, of course we can do this. I was looking at something incorrect in my notes. Sorry. I was testing you. Yeah, I can totally do this. Can we edit this? Sorry. Just cross it out. Just cross it. Is that what you were gonna say, Julie? Yeah, okay, I'm so sorry. Guys are absolutely right. I'm just checking if everybody's paying attention. So Hamilton cycle, let's write it down. I'm so sorry. We can definitely do this. So let's try again. I'm just gonna start at A. I'm gonna go to B, to C, to F, to I. I'm going around the outside until I get to H, to G, and then finally I'll jump into the center and hit E before I go over to D. And then, well, actually, I could go over to D before I go to E if I wanted to. Let's just do
Yeah.
that. Stay all the way on the outside, G to D, then I'll sneak into E and then go to A. Sorry, there is a Hamilton cycle there. My bad. What I meant to do was show you a different graph. That should be minus something. So here is another example. This is the one that I meant to draw up here a moment ago. So here's my little graph. This is a much smaller one that has a central vertex again, but just one edge kind of crossing through it. A very small little graph here. Okay, let's look at this one and see if I can get the right answer this time. So we have 5 vertices. It's just a square that has a diagonal on one end of it with a point in the middle. So if we wanted to, we could start with a Hamilton path again. So same question as before, is there a Hamilton path? Let's try to write it down. You can just make a Z for this, right? You start at A, go to B, then cut through the center, go to C, go to D, go to E. A, B, C, D, E. That's fine. And that would be a perfectly reasonable Hamilton path. But there is no Hamilton cycle here. That's what I meant to write on this graph. This one actually does not have a way of getting back to where you started. And now I'm going to write down some observations to help us understand why can't we do it. Because this is actually not going to fall in the heading of a simple theorem. And so instead of like a one size fits all theorem for this, I'm going to have to make a bunch of observations that we kind of collectively try to use to help us with these kinds of questions about Hamilton paths and cycles. So the first one is that for each vertex, okay, maybe before I write it down, let me just say it. For each vertex, if you're only going to visit that vertex once, then that means that you will only be using 2 of the edges that touch up with that vertex, that are incident with that vertex, right? So when I visit vertex D, so if let's just do our Z pattern here, right? This was the Hamilton path that we had. But notice that in the vertex D, I'm only visiting it once. So although there's 3 edges there, I only will use 2 of those edges. One to arrive on and one to depart on. Is always going to be exactly 2 edges. So we'll just point that out. First of all, exactly 2 edges. Incident with it will be used by the Hamilton cycle. This is for a cycle. Okay, obviously the vertex A, since I wasn't returning to vertex A, I only used one of the edges that was incident with vertex A. So it's just for cycles. And then the second observation is kind of related to that. So if you're trying to go through your graph and make your Hamilton cycle, and you've visited a vertex and used 2 of those edges, then you can remove all of the other edges that are incident with that same vertex. You're not allowed to use them. Because if you used any additional edges besides the 2 that you've already used, you would be forced to visit D, for example, a second time, which we're not allowed to do. So let's just write that down. Once 2 edges have already been used, right, none of the other edges. All right, in this case, then none of the other edges can be used. And that would be for a path or a cycle if you were creating it. Once you've used two edges that are incident with a vertex, you can't use any of the others. And kind of as a consequence of that, I'll make one more observation, which is also extremely helpful, which is that a Hamilton cycle cannot contain a premature sub-cycle. I'll explain what I mean here. A Hamilton cycle cannot contain a premature sub-cycle. Let me draw the graph again. You guys might even want to draw it again in your notes here. We're just going to draw the same exact picture. I want to kind of start fresh again. Just do it like so. So we have A, B, C, D, E. So if there was going to be a Hamilton cycle here, if there was, but I already made the point that there isn't. But if there was, this is going to be proof by contradiction. How do you show something doesn't exist? Well, you suppose that it does exist, and then you make observations about this hypothetical Hamilton cycle, right? This hypothetical Hamilton cycle would have to visit vertex A, which means it would have to use both of those two edges, right? But it would also have to visit vertex E, which means it would have to use this edge as well as this edge, right? Now that is going to be a premature subcycle. And what I mean by that is that, well, we've got a cycle that has not visited every vertex. Why is this a problem? Well, it's a problem because, you know, if you're going to go around all four of those vertices, any attempt to visit other vertices that are not yet included would involve creating or using additional edges that have to connect to the vertices you've already used up all the edges for. You see what I mean? So if you have it, and then you'd be, you know, visiting D twice, for example, something like that. So that's kind of what this third point is saying. I'm not stating any of this as a theorem. It's kind of more just observations more than anything else. But this is the kind of reasoning that we have to do with Hamilton cycles. There isn't just a simple theorem to be applied in this case. You also generally can't just look at a graph. Like, you know, we just looked at this, found the degrees of the vertices, and we knew, oh, there's going to be an open Eulerian trail. But in terms of Hamilton cycles, you usually can't just glance at it and tell right away, unless it's a really, really simple graph. Okay, so these are kind of observations that will help you rule out the existence of a Hamilton cycle. Okay, so if there is a forced premature subcycle that you have to have, like in this graph, right, then you cannot have a Hamilton cycle. If you're going to have a Hamilton cycle, exactly two edges that are incident with it would have to be used. So if you have for example, a vertex that only has degree 1, then you can't have a Hamilton cycle. Right? Yes, Julie.
That example
This one?
cannot have a premature cycle.
How you mean how it would have to have a premature? Oh, so did we write down a Hamilton cycle? We wrote this one down. So if we look at that, and I guess I didn't draw the last edge here, if we just look at this blue path that we've traced out, we can just look and say it doesn't have, I mean, you can see it's basically this shape, that. There is no subcycle within this. If I just take this shape, so I have all these vertices here. So that doesn't mean that we couldn't try something else and end up creating sort of a subcycle where we haven't visited everything yet. But all that proves is that attempt didn't work. And we didn't choose a good set of edges and vertices. But as long as we can find one way to do it that does work, then we're fine. Yeah,
Thank you.
yeah. Maria?
So when we were doing the Eulerian Trail.
Yes.
And like you said, we can't really go wrong because if we had a problem like this cycle, then we could insert cycles.
Right, we can insert subcycles.
It's like if you do go which way, that's
Yeah, well, or you just, yeah, like here, if you are forced to go around the outside of the square, right? So it's not really that you did anything wrong, it's just that you have no way, so you've used all those edges. Because you were forced to use them by visiting A and E, and you haven't visited all of the vertices yet. So you don't have a full Hamilton cycle yet.
But even if we, sorry, just on the, if we repeat.
One more time, if we didn't.
If we go through like, you know, still like. Can we?
Yeah, I mean, we could say, okay, this is a premature subcycle, so I can't make this work. And you could say, well, what if I change my plan? Because I know, oh, I have to visit vertex C. Is this kind of what you're getting at? So then I would say, all right, sure, go ahead and visit vertex C. Now, good luck getting over to E,
Yeah.
right? So you're in trouble that way as well. And you could also say that that's a forced premature, maybe I should say, put that word here, contain a forced premature subcycle. You are forced to make that subcycle because there are a lot of vertices of degree 2. And so you have to use certain edges. And if those edges collectively make a cycle that doesn't use every vertex, well, then you're not going to have a Hamilton cycle there. Yeah, Nikolai?
I'm just thinking like, is it because when you do this, what did we do?
Yeah.
Go A, B, C, or sorry, A, B, C, B. There's only one way to get back to A particularly, and that's what it is.
That's basically it. Yeah, that's basically it. That's basically it. So the real downfall of this graph is that there are a lot of low degree vertices. And so you're forced to use, because every time you want to visit a vertex, right, you have to use 2 edges that are incident with that vertex. And you can see that since there's a lot of vertices of degree 2 here, that you are forced to use too many edges. You cannot actually make a Hamilton cycle. So when you're looking at the list of observations here, we're just going to kind of wrap up for the day. When you're looking at these observations, these are all observations to help you understand why you wouldn't have a Hamilton cycle in a graph, right? What you might be wondering right about now is, are there any characteristics where you would be guaranteed that a sufficient condition exists that there will be a Hamilton cycle? In other words, turn this question around. Is there something that would give us a positive conclusion? Say, yeah, if we notice this about the graph, then yeah, there will be a Hamilton cycle. And it turns out that there are such conditions. As you could maybe suspect, they have to do with having vertices of high degree. If you have vertices of high degree, well, then that's great because you have lots of flexibility with how you visit all of the vertices. But what we don't actually have, my friends, we don't even have this at all, is an if and only if characterization. So I'm gonna, on Thursday, write down another list of some things that would be sufficient for having a Hamilton cycle, but they're not connectable to those observations. So we have to kind of play both sides of this equation a little bit to understand how this works. And by the time we're done with this by Thursday, we're gonna have some pretty big graphs in front of us. And I'm gonna have you guys probably do some group work on Thursday, where you try to answer the Hamilton cycle question. It's a famous problem. And it's also a very important problem. So I encourage you to keep exploring this, but I'm gonna call it a day for today and wish you all a wonderful rest of your Tuesday. Quick reminder, I am gonna be heading out early today. So if you need to talk to me, try to do so on the sooner side.